So again, we'll be talking about gases, and if you didn't already know, our atmosphere is made of gases. Specifically, the gases our atmosphere is made up of is oxygen and nitrogen mostly. It's about 70%, 78%. Sorry, it's about 78% nitrogen, about 21% oxygen, uh, and the rest of it is made up of other gases like argon, carbon dioxide, water vapor, and such. But uh, that's a common misconception. A lot of people think that our atmosphere is made up mostly of oxygen. It's actually mostly made up of nitrogen. Um, so yeah, if we had like 100% oxygen in our atmosphere, that would be really bad because a lot of things would catch on fire. Because oxygen is the fuel for fire. The slightest spark would explode. So it's a good thing that our atmosphere is basically it's mostly nitrogen rather. So since we're talking about gases, let's talk about some properties of gases here. Um, the property of the gases are dictated by what we call the kinetic molecular theory, and basically what this really means is that gas molecules will move rapidly in straight lines. They have very little attractive forces, so they mostly repel each other, and they are very far apart. Right, gases are very far apart. Those gas molecules are very far apart. And an important distinction to be made also with gases is that they actually have very small volumes compared to the containers that they occupy. And the kinetic energy that resides in gas molecules increases with an increase in temperature, kind of like a hot air balloon, right? And expands a hot air balloon. So when we talk about gases, there are things that certain properties or variables that we need to always take into account. The first of which is pressure, right? And pressure is the force that a gas exerts against the walls of its container, right? The force it does. So the units that we use to measure pressures is either the atmosphere, millimeters mercury, the torr, or the Pascal. And then the next property is volume. That's pretty self-explanatory. It's a space that is occupied by the gas. That's always liters and milliliters, like you already know, like just like liquids. Temperature is important too. Uh, it's the it's important in determining the kinetic energy that's in the gas particles, right? And of course, uh, like I was saying before, in chemistry, we most commonly use the unit Kelvin, uh, but sometimes there's Celsius too. But most commonly we use the unit Kelvin. And then the amount or the number of moles of gases is also important too. A property that we observe when we study gases. So, how do we determine the pressure of gases? We use an instrument called a barometer, and uh, barometer was invented by I don't know how to say his first name, Evangelista Torricelli. That was the last name was easier to say. And the important thing to know about how a barometer works is that there's a column of mercury, right? And at exactly one atmosphere, the column of mercury is 760 millimeters high. So basically, the mercury is in this little like dish, and the atmosphere pushes down on the mercury, and when it pushes down on the mercury, if there's one atmosphere, right, of pressure, that mercury is pushed up into the glass tube where there's a vacuum, right, and the column is 760 millimeters mercury in length or height. So we can use that as a conversion factor then, because one atmosphere then equals 760 millimeters mercury, or also equals to 760 torr, all at sea level, right? And the chart at your right is basically the chart at your right is basically the conversion factors for all the different units that we use to measure pressure. So there are several different gas laws that we need to actually learn about before we can study gases. And the first one is called Boyle's Law. And Boyle's Law states that when the temperature is constant and the amount of gas is constant, the pressure and the volume is also constant, right? So you can extend that to say then that if a volume decreases, then the pressure increases, giving you this formula down here, where if you have the initial volume and the initial pressure, it will equal the uh, uh, final pressure and the final volume. And so let's put that into work, right? Into some work here. We have a piston, and this piston is exerting is uh, determining the volume for this particular cylinder. And at the initial position the piston is at, the volume is 4 liters, right? And when at the volume of 4 liters, the initial pressure is 1 atm. If we cut that in half, as you can see here, with the final volume, right, being 2 liters, then the pressure becomes 2 atm, or 2 atmospheres, right? That's where we get this particular um, formula from. Okay, that's where we get this particular formula from. So if you have an initial pressure, and you have an initial volume, and you have a second or a final volume, then you can determine what the new pressure is going to be by solving for pressure 2 or final pressure, right? This can actually be demonstrated very aptly by the way our lungs work, right? Um, During inhalation, right, our lungs expand. The pressure in the lungs it decreases, right, because our lungs are expanding, and the air flows toward the lower pressure in the lungs. Um, and so, and then during exhalation, the lungs volume decreases and pressure within the lungs increase, right? And the air flows from higher pressure into the lungs to the outside. Sorry, from the lungs, from the higher pressure to outside where it's lower pressure. So that's basically how your lungs work. And then just talking about weather too, because of our recent weather catastrophes. Um, if you ever wonder why it's so windy here in the DFW area, it's because oftentimes we are sitting below a low pressure front, right? Which means that the area above, or the atmosphere above Dallas or DFW, is in a low pressure area, right? And so whenever there's a high pressure system around us somewhere, that high pressure flows of gas flows into the low pressure, and that's what causes wind. So yeah, this Boyle's law is actually evident everywhere we look. The next law to talk about, before we can talk about the next law, we need to actually practice some Boyle's law problems, right? So the question says, a sample of oxygen has a volume of 12 liters and 600 millimeters mercury in pressure. What is the new pressure when the volume changes to 36 liters at constant temperature and number of gas particles, right? So what do you do here? Well, first thing to do is you identify the equation you need, which turns out to be the Boyle's law equation, the one we just went over. P1V1 equals P2V2, right? P2V2. We have an initial volume, and we have an initial pressure. We have a final volume there. So now we need to figure out what the new pressure is. So that's going to be P2, this new pressure. So let's rearrange the equation. When we rearrange the equation, P2 equals then P1 times V1 over V2, right? So then we can do some quick dimensional analysis, right? P2 equals 600 millimeters mercury, right? 600 millimeters mercury. And then the V1 is at the top, which is the initial volume, 12 liters, right? And then the new volume is at the bottom, 36 liters. So this expanded, right? Forgot to put my zeros in there, right? Liters cancel, leaving you with just millimeters mercury for the new pressure, and that gives you 200 millimeters mercury. Gives you 200 millimeters mercury. Pretty simple, right? And notice that as the volume increased to 36 from 12 liters, the pressure decreased. And it makes sense, right? Because now you have more space for the gas to collide with things, right? All right, let's try another one. I have some helium gas, and it has a volume of 120 milliliters at a pressure of 850 millimeters mercury. The pressure changed to 425 millimeters mercury. So what is the volume then? Again, we'll identify the equation we need to use. P1 V1 equals P2 V2. We need to rearrange the equation, right, so that we can solve for V2, because this right here, the new volume right here, is V2, right? So V2 then equals V1 times P1 over P2. Okay. Again, some quick dimensional analysis. V2 equals 120. That looks like 120, right? I'll just write it again. Equals 120, right? Milliliters. And we'll have our new volume here. Oh, sorry, our initial pressure here, 850 millimeters mercury. Oops, I don't know why I'm writing twos instead of G's. And then 425 is the new pressure. Right. The pressure decreased, right? Which means that we're going to have a volume that is less than the initial, right? Or sorry, a volume that's greater than the initial, right? Because the pressure decreased. And so if you cancel the millimeters mercury out, and I didn't realize that my head is blocking the thing, so let me just clear off my head real quick. There we go. We cancel out millimeters mercury, we're left with a volume, right? And then some quick math here, we get 240 mils. See? So notice, when the pressure decreased, the volume increased. Right? Same principle as the last question. Okay. Let's bring myself back. There we go. So the next gas law that we have to learn about in our study of gases is called Charles's law. Like I was saying before, when we do chemistry and we talk about temperature, we're always using Kelvin as the unit for temperature, right? And Charles' law says that the temperature of a gas is directly related to the volume of the gas. So what that means then is that if you have a gas that is a certain temperature, say for example at 200 Kelvin at its initial temperature, its volume, say, is 1 liter. But if you increase the temperature by double, 400 Kelvin, and what will happen? Well, the volume of the gas will double to 2 liters, right? Will double to 2 liters. So that's what that means when it says directly related. Of course, we keep pressure and the moles of gas constant. This only has to deal with temperature and volume, right? And that's basically all you need to know about Charles' law. So let's go ahead and do a couple of practice problems with Charles' law. So a balloon has a volume of 785 milliliters, right? So that's going to be V1, right? And then it's at 21 degrees Celsius, which is T1. We want to drop the temperature down to 0 degrees Celsius. This is T2. And then what is the new volume? Which is V2. Well, the first thing we have to do is convert the Celsius into Kelvin, right? So for T1, 21 degrees Celsius, converted to Kelvin, all you have to do is, of course, add 273 and that gives us 294 Kelvin, right? And then for T2, we're at 0 degrees Celsius. Again, add 273, and that's 273 Kelvin for 0 degrees Celsius, right? So that's how we convert Celsius to Kelvin. Don't forget to do that. And then we can use Charles's law to solve for the answer here, to solve for the final volume, right? If you remember Charles's law, that is the one that is V1 over V T1, and then V equals V2 over T2. Okay. We can rearrange that then to say V2 equals V1 times T2 over T1, right? It's that simple. Some quick dimensional analysis again. V2 equals the initial volume, which is 785 mils, right? And then T2 is at the top, which is 273 Kelvin. T1 is at the bottom, 294 Kelvin, right? So the Kelvins cancel, and you get 729 milliliters. Right? 729 milliliters. 729 milliliters, right? So as you can see, what happens when you when you decrease the temperature, right? The volume decreases. Direct relationship. Vice versa, if the temperature increases, the volume increases. And that's what Charles' law says. All right, let's do another Charles' law example. Oops. Can't really read what that says, so I'm going to have to clear off my previous example. Here we go. I have a sample of oxygen that is a volume of 420 milliliters at 18 degrees Celsius. All right, so again, V1, T1, and we always have to convert this to Kelvin. Okay. And then now it's asking for what the temperature is in Celsius when the volume of oxygen becomes V2 here, 640 mils, right? And again, pressure and number of moles are constant, of gas is constant, right? So here it's asking for you to give the answer in degrees Celsius. So technically you don't have to convert to Kelvin first, but you should, because that's how we do all chemistry formulas, right? So let's go ahead and convert it to Kelvin. 18 degrees Celsius plus 273 equals 291 Kelvin, right? We can rearrange our Charles' law equation again, and now T2 equals T1 times V2 over V1, right? My T over here looks weird. There we go. There we go. So some quick dimensional analysis again. T2 equals 291 Kelvin, and then this time V2 is at the top, and that was 640 mils, and then V1 was at the bottom, which was 420 mils, right? Mils cancel out, leaving me with Kelvin, and you have 443 Kelvin as your answer, right? And then to get it back to Celsius, all you have to do is subtract 273, right? So that's 0, borrow 1 here, and 7, right? 107 degrees Celsius is your answer, right? 107 degrees Celsius. Cool. So the next law in our repertoire of gas laws to learn about is called Gay-Lussac's law. And let me change the slide here. There we go. Gay-Lussac's law. And Gay-Lussac's law deals with pressure and temperature, right? It says that the pressure exerted by a gas is directly related to the temperature of the gas. So very much like the Charles law, which said that volume and temperature were directly related, Gay-Lussac's law says that temperature and pressure is directly related, which makes sense, right? Because here you have a cylinder with a piston again, and it's being held at 200 Kelvin, and at 200 Kelvin, its pressure is 1 atm. You double the temperature to 400 Kelvin, and you double the atmospheres or the pressure to 2 atm or 2 atmospheres, right? Of course, again, constant being held here are volume and amount of gas, or number of moles of gas, right? So I do have this one question to ask you then. Explain why then water boils at a lower temperature in the mountains than at sea level, right? At sea level. Well, water's boiling temperature or boiling point is 100 degrees Celsius, right? Or 212 degrees Fahrenheit. And that's at sea level. But as you increase the altitude, right, like by going up into the mountains, right, there's less pressure above you, right? And if there's less pressure above you, you don't have to reach as much energy to be able to evaporate, right, to actually boil water. Because the pressure exerted on the surface of the water needs to be overcome for the water to boil, right? And that's why it's easier to boil water when you are, or actually, I should say, water boils at a lower temperature at a higher altitude, right? I wouldn't want to say it boils easier, because at a higher altitude it's also colder too. So let's do some Gay-Lussac's practice questions. Right. So we have a gas that's at a pressure of 2 atm, right? So that is P1, right? That's totally P1 right there. And then we have it at a temperature of 18 degrees Celsius, right? That is T1. Okay, again, don't forget to convert this to Kelvin. Gotta make that Kelvin. And then, so what is our new pressure, which is P2? I don't know what happened to my 2 there, I got messed up. There we go, P2. When the temperature now is at 62 degrees Celsius. This is T2, right? Again, this needs to be converted to Kelvin, okay? How do we do that? Very simply, we've already done it many times. T1 equals 18 degrees Celsius plus 273 Kelvin, right? Or just 273, and that equals 291 Kelvin. And then T2 equals 62 degrees Celsius plus 273, and that's 335 Kelvin, right? And then, if you recall, Gay-Lussac's law, or its equation, is P1 over T1 equals P2 over T2. Okay, we can rearrange that for P2 to solve for P2, and that equals P1 times T2 over T1. Simple as that. All right. Now let's plug in some stuff. P2 equals 2 ATMs. And then T2 is at the top, so it's 335 Kelvin. T1 is at the bottom, that's 291 Kelvin. Right? The Kelvins cancel, and we're left with 2.3 atmospheres. Right? 2.3 atmospheres. Right? So notice as the temperature increased, right, so did the pressure. It also increased. Let's see another practice problem here. Oh look, I didn't even write over the new question. I have to erase it out like I did on the last one. Okay, so a gas has a pressure of 645 torr. That is our P1, right? That's our P1. And then its temperature is 128 Celsius, right? So that is our T1. It's asking for the temperature now in degrees Celsius. That is our T2. And then the 824 torr is our, oops, not the P2, right? Again, no, I know it's asking for Celsius, but we always do everything we do everything in Kelvin when it comes to temperature. So T1 equals 128 degrees Celsius plus 273 equals 401 Kelvin. We'll rearrange Gay-Lussac's law again so that T2 now equals T1 P2 over P1, right? That's an X right there, right? So T2 equals 401 K, and then P2 is at the top, right? And that would be the 824 torr. Oops, 824 torr, right? And then P1 is the initial temperature. Initial pressure, which was 645 torr. And then that gives you 512 Kelvin. Didn't even see that. Let me write that again. That gives you 512 Kelvin. Let's convert that back to Celsius. Minus 273, right? And that means then the answer is 239 degrees Celsius. Right, 239 degrees Celsius. So now we can take all the gas laws we just learned and bring them together into what we like to call the combined gas law, right? And the combined gas law takes Boyle's law and its relationship with pressure and volume, Charles's law with its relationship between volume and temperature, and Gay-Lussac's law, which involves pressure and temperature, and combines them all into what we call here the combined gas law equation, right? We can use this equation now to solve for different gas properties, right? So let's start out with this particular example here where we have a gas with a volume of 675 mils. That's V1. And it's at 35 degrees Celsius, which is T1. and its pressure is currently at 646 millimeters mercury, which is P1, right? And it's asking for the volume, so that's going to be V2. That's what we're solving for. At a temperature of negative 95 degrees Celsius, which is T2, and then a final pressure of 802 millimeters mercury, which is P2. Well, the first thing we have to do, as always, is convert our Celsius to kelvins, right? So T1 equals 35 degrees Celsius plus 273, and that gives us 308 degrees Kelvin, or sorry, 308 Kelvin. Not degrees Kelvin, just Kelvin. T2 is negative 95 degrees Celsius plus 273, and that gives us 178 Kelvin, right? And recall, we are looking for V2, solving for V2, so we have to get V2 over here in the combined gas law by itself. We can rearrange the equation with some arithmetic and some mathematics, and we get V2 equals V1 times P1 over P2 times T2 over T1, right? So some quick dimensional analysis again. V2 equals then 675 mils I have to fix my L there. Looks weird. There we go. And the pressure, initial pressure is at the top, so that's 646 millimeters mercury over 802. Write that again, 802 millimeters mercury. There's two M's there. There we go, millimeters mercury. And then for the temperature, final temperature is the top here, so that's 178 Kelvin over 308 Kelvin, right? Millimeters mercury cancels, Kelvin cancels, leaving you with just mils as the volume. And we'll do the math, and we come up with 314 mils of the gas, right? It's that simple with the combined gas law. So we've taken into account everything, all the gas properties, pressure, volume, and temperature, except for one, and that is N, or number of moles, and that is covered by Avogadro's law, right? So Avogadro's law says, as you would assume, or you can imagine, that the number of moles of a gas is directly related to the volume, right? Which means the more moles of gas you have, the more number, the bigger the volume is that gas takes up. Self-explanatory, right? Again, here temperature and pressure are constant. So if you start out with 1 mole of gas at 1 liter of gas, and you increase it to 2 moles of gas, you'll get 2 liters of gas, right? Direct relationship there. So let's do a quick example problem. We have 0.75 moles of helium, right? And it occupies a volume of 1.5 liters. Okay. So this is N1 right here for the number of moles of helium, and this is V1 right here for the volume, right? It's asking for what volume? So that's going to be V2. And then here is N2, which is 1.2 moles of gas, right? At constant temperature and pressure, right? So we rearrange this equation, and we get V2 equals V1 times N2 over N1, right? Luckily, there's no temperature to convert this time, so it's a pretty simple one. V2 equals 1.5 liters, and then the number of moles, the final number of moles, and 2 is at the top, so that's 1.2 moles, over 0.75 moles of gas, right? Moles cancel, right? And we do the quick math, and it's 2.4 liters is the new volume, right? So notice we increased the number of moles from 0.75 to 1.2, and correspondingly the volume increased from 1.5 to 2.4 liters, right? So that brings us to standard temperature and pressure and its relationship to molar volume, right? So STP stands for standard temperature and pressure, like I already said, and these are certain conditions in which the standard temperature is either 273 K or 0 degrees Celsius, right? And the standard pressure is 1 atm or 760 millimeters mercury, right? And at those conditions, those standard temperature and pressures, right? 1 mole of a gas occupies 22.4 liters, right? We call that the molar volume. Okay. So at standard temperature and pressure, 22.4 liters of gas equals 1 mole of gas. We can use that as a conversion factor here, where 1 mole of gas over 22.4 liters, or 22.4 liters of gas over 1 mole of gas, right? So let's do a problem involving STP. So what is the volume occupied by 2.75 moles of nitrogen gas at standard temperature and pressure, right? Pretty simple here. We start out with our 2.75 moles of gas, nitrogen gas, moles of not H N2, right? We know it's standard temperature and pressure, so these are all the givens here, right? 273 Kelvin, 1 atm, 22.4 liters, right? So we can use that now as a conversion factor. We want to get rid of moles and go to volume. So we'll put, for every 1 mole, right, of N2 gas, what do we have? Well, over there, right? 22.4 liters of N2 gas, right? Do the quick math on that there, and we get 61.6 liters of N2 gas. So standard temperature and pressure problems are pretty simple because you know everything already, and you're just going straight to either moles of gas or liters of gas, right? So when you have a mixture of gases, we have to then talk about Dalton's law of partial pressures, because each gas exerts its own pressure inside of a container. Okay, so the total pressure right here is equal to all the other pressures combined, right? So P1 is a gas, let's say hydrogen gas, and then P2 is nitrogen gas, P3 is oxygen gas, and so on and so on. All those pressures added to each other will equal to a total pressure, right? So in a pure gas, let's look at these examples real quick right here. We have 1 mole of gas, 1 mole of nitrogen gas, and it exerts 1 atm of pressure, right? But in our gas mixtures, we can have 0.4 moles of oxygen and 0.6 moles of helium, giving us 1.0 moles of combined gases, right, of oxygen and helium, and that also gives us a total pressure of 1 atm. We can combine 3 gases oxygen, helium, argon at 0.5, 0.3, and 0.2 moles to equal a total of 1 mole of gas, and that also exerts 1 ATM. All right. So let's do a quick practice problem. I have to clear out all my writing there because I wrote over the question. Can't even read it. There we go. For a deep dive, a scuba diver uses a mixture of helium and oxygen with a pressure of 8 ATM. All right. If the oxygen has a partial pressure of 1280 millimeters mercury, what is the partial pressure of the helium? Right? And again, we're only talking about pressures here, so volume and pressure, temperature are constant. Right? So let's write out the partial pressures equation. Right? So we have P total. That equals the partial pressure of O2 plus the partial pressure of the helium. Okay. So of course we have to do something here to match the units. We have ATM here, right? But we have millimeters mercury here. Right? So let's do some quick conventional conversions or dimensional analysis, right? So convert P units to match. So let's start out by doing 80 ATM. For every 1 ATM, there is 760 millimeters mercury. Okay. So that gives us 6,080 millimeters mercury. So now we have them both in millimeters mercury. And it's as simple as doing some quick arithmetic here. We're looking for the partial pressure of helium, right? So we need to rearrange so that partial pressure of helium is by itself. So P helium equals the total pressure minus pressure of O2, the partial pressure of O2. So then P partial pressure of helium equals then 6080 minus 1280, and that gives us 4800 millimeters mercury for the partial pressure of helium. Pretty simple, just easy arithmetic. Easy arithmetic. And that pretty much concludes what I want you to know about gases. I know it seems like a lot, but let's move on. So now we'll talk about solutions, right? There are 3 types of solutions. We have gaseous solutions. We have liquid solutions, which is what you're probably most familiar with. And then we have solid types of solutions, right? Solid solutions. Excuse me. And just to talk about the gas solutions, we were just talking about gas solutions where, we were talking about in the previous question slide where we had a question where it was like a mixture of oxygen and helium, right? And they had partial pressures, and that is a solution of gas, right? So the example they're showing here, though, is in our environment, right, where oxygen and nitrogen compose our atmospheric gases mostly, right? And since there is more nitrogen gas than there is oxygen gas, right? Remember, there's only like 21% oxygen in the atmosphere, and I think it was 78% nitrogen, right? That makes that the solvent here is nitrogen gas, because it's the one in the most abundance. And the solute, right, is oxygen, because it's the one with the least abundance in the atmosphere, right? The same principle can be held with solutions of liquids, right? A good example here of a gas being dissolved in liquid is soda water, or in Texas we call it Coke. It doesn't matter what kind of soda it is. We just call it Coke. And water is the solvent here, because soda is mostly, or Coke is mostly made of water. And the gas dissolved in there as the solute, right, is carbon dioxide gas, right? Household ammonia, like Windex or something, right? That's ammonia gas as a solute, or dissolved in the solvent of water again, right? We have some liquid and liquid solutions too. Vinegar, household vinegar, which is just acetic acid as a solute, right? Acetic acid. That's acetic acid's formula if you didn't know. HC2H3O2, right? And it's dissolved in water. Water is a solvent, acetic acid as a solute. Oh, here's a good one. I have a saltwater fish tank at my house, right? And I use water, and I dissolve a whole bunch of salt in there. So salt is the solute there, right? And then we can move on to solid solutions, right? And this is mostly like metal alloys, right? Where brass is made up of zinc and copper, right? And in this case, there's a lot more copper than there is zinc in brass. So zinc is the solute to copper's solvent. Steel, another common one, right? We have carbon in steel as a solute to molten or to iron, right? That's why most steel is called carbon steel, right? That's what makes iron stronger, by the way, adding carbon to it, okay? So you notice up here, though, wow, water is used a lot as a solvent. In fact, it's known as the universal solvent, right? That's why I actually have the picture up here in the upper right-hand corner, right? Because when you look at water, if you remember here, this water molecule, right? It's a polar molecule. It's one of the most polar solvents, and it's also known as the universal solvent. I think I said that a second ago, right? Because when you look at water, right, that's what it looks like. And the negative side is over here, right? Partial negative side is over there. And the hydrogen side is the partial positive side, right? What's really cool about that, if you recall, from when we were talking about hydrogen bonds, is that high water can form a hydrogen bond with another water, right? Because this is a partial positive here. Right, and this network of hydrogen bonding can happen with all the water molecules in the solution. Hydrogen bonding, or bond, right? So most of the time when you have some kind of reaction, chemical reaction occur, it has to happen in some kind of solution, right? And most commonly in life, the reactions that make us alive, that keep us living, occur in water, right? Occur in water. So here, water is dissolving salt, right? How does it do that? Well, remember that salt is made of sodium and chloride, right? Chloride is on the right side of the periodic table, so it's got a negative charge, right? Because it accepted an electron from the sodium, right? And sodium is on the left side of the periodic table, so it's positive. Okay? So the water molecules, with their partially positive / partially negative selves, polar selves, right, will go in and separate out salt molecules, right, and or separate salt into its substituent ions, where the oxygens of the water will surround the positive ion because the oxygens are negative. Right? That's really dirty. Let me write that again. So we have sodium, which is positive, right? Because it's on the left side of the periodic table, and it lost an electron to chloride, to chlorine to make chloride, right? So when water gets in there, right, to dissolve it, it breaks up all the ions, right? And the oxygen side of the water surrounds the positive sodium because the oxygen is the negative side of the water. And then the opposite happens with the chloride, right? Because the chloride is negative, right? The chloride's negative. And so here, the hydrogen side surrounds the chloride ion, right? And there's another one down here, but you can't see it because my head's blocking it, right under the chlorine, right? And that's how water dissolves ionic compounds, right? That's how water dissolves ionic compounds. So there are a couple of things to keep in mind here when you're talking about solutions, right? And there's this phrase that I like to say that is likes like, right? Like likes like. Okay? So what that means is that molecules or chemical compounds that are similar, right, tend to like to dissolve each other. And the thing is, that phrase has been evolved over many years. It used to be like dissolve likes, like dissolves like, which is true. And then it became like likes, or like likes like, which it likes, things that are similar to itself. But now, I think the phrase has evolved into the phrase like seeks like, right? And all that is to mean that solvents that are polar, right, tend to like to dissolve polar solutes, right? And then solvents that are nonpolar tend to like to dissolve solutes that are nonpolar, right? So if you think about it on the other side, right, a nonpolar solvent will not be able to dissolve a polar solute, right? And then a polar solvent will not be able to dissolve a nonpolar solute, right? So in the case of water and salt here, you have water, which is polar, like I showed you before how polar it is, right? I'll draw it again since I have to erase it. Partially negative down there, partially positive up there, right? And then we had salt, which is obviously positive on one side because of sodium, and negative on the other side because of the chloride. So like, right? Or polar solvents dissolve um, uh, polar solvents dissolve polar solvents, right? Now, if you were to put a non-polar uh, molecule in there to try to dissolve in water, it'd be a lot more difficult, right? And everything has its own different solubilities based on its properties, but let's compare this to something super similar to salt, but not really, right? Sugar, for example, right? Sugar is not an ionic compound, it's a molecular compound. It's glucose, right? Glucose, well, it's sucrose, which is a glucose and a fructose put together, right? And I can tell you now, and we'll talk a lot about that later on too when we're talking about glucose metabolism and later on in the lecture or later on in the semester. But glucose, or sucrose rather, sugar, table sugar, right, doesn't dissolve as easily in water as salt does, right? How many times have you tried to dissolve sugar in your unsweet iced tea? It takes a minute, right? It makes it easier when the tea is still hot, right? But once it's cold, it's pretty difficult to dissolve dissolve the sugar in the water, and that's because sugar is much less polar than salt is, right? So keep that in mind. Like, but also keep in mind too that opposites attract, right? So when you're talking about solutions, solvents and solutes, like, right? Things that are similar to each other will dissolve each other, right? But if you're talking about the periodic table and cations and anions, right, to make ionic compounds, in that case, it's opposites attract, right? That's a little rule of thumb to remember. So, in talking about solutions, let's talk about electrolytes. Okay, let's talk about electrolytes, right? So, like I was saying before, water dissolves salt readily, like sodium chloride readily, right? So, in this particular equation, we can write an equation for this occurrence, NaCl, right? And add some water to it. Forgot the solid state there. And we come Na plus aqueous plus Cl minus aqueous. Okay? And it pretty much completely goes into solution, like it dissolves completely, right? 100% dissociation. I always forget how to spell dissociation. There we go. Dissociation, right? That means, what does dissociation means? That means that the water dissolved the ion, right, and split it into its substituent sodium cation and its chloride anion, right? That's what dissociation means. And since salt dissociates so readily in water, right? So readily in water, it can produce a very strong electrolyte, which means that it can, if you run a current through it, it will complete a circuit of electricity, right? And you can power a light bulb very brightly. And just, that's the word I'm looking for. Self-explanatorily, right? When you're talking about electricity, right, you have a positive electrode and you have a negative electrode, right? And the chloride ions are drawn towards which are negative, are drawn towards the positive electrode. And the positive ions, the sodium ions, are drawn towards the negative electrode, right? So that's what we call a very strong electrolyte. We also have a weak electrolyte. So here we have hydrogen fluoride gas, right? Hydrogen fluoride. HF. AQ. With some water. And it becomes H plus F minus. Right? Hydrogen fluoride gas. But this is a weak electrolyte. It doesn't dissolve in water as well as salt does. Why? Because salt is definitely way more polar than hydrogen fluoride is, right? So generally we see an arrow that goes to the right making products, but since this is not a complete dissociation, right? We have to have an arrow going backwards too, where this is a recombination. In fact, when you're talking about hydrogen fluoride, right, or hydrofluoric acid in this case, right, because it's in water, most of it stays together as hydrogen fluoride and doesn't break into the substituent hydrogen uh, uh, ion, H plus, and the fluoride ion, F minus, right? So it only dissociates slightly in water. Slight, slightly, slightly, slight. I did it again. What the heck? Slight. Is that slightly? Maybe. It looks weird to me. Anyway. And so since it only dissociates slightly in water, you get a much weaker electrical current being passed through. And so the light bulb doesn't light up as much, right? And then over here we have a non-electrolyte in which we add methanol into water. And when we add methanol into water, methanol is non-polar. Well, methanol is slightly polar, right? Because it has an oxygen in it, but when compared to actually polar compounds, methanol doesn't come anywhere close, right? And so when it goes into water, since it's so much less polar than other things, right, it pretty much stays together as methanol molecules in the water. It doesn't split up at all. There's no charge, right? There's no charge at all. So when it dissolves in water, it stays as methanol. It doesn't go into its substituent ions, right? Because it's a molecular compound. It's not even an ionic compound, right? And so that makes it a non-electrolyte because when you try to pass a current through it, no electricity passes through, and the light bulb stays off. And that's basically what electrolytes are. And then since this is an allied health emphasis class, I would be remiss in my duties if I didn't mention the fact that electrolytes can be referred to as equivalents, right? So an equivalent is an amount of electrolyte or an ion that provides 1 mole of electrical charge, right? Positive or minus in a solution, right? The charge of the positive ions is always balanced by the charge of the negative ions. That is true. That's always true. And the concentration of electrolytes in the intravenous fluids, like saline solution, right, are expressed in milliequivalents per liter. So MEQ per liter, right? So one equivalent equals 1,000 milliequivalents, right? So this chart I have up here on the upper right hand corner, right, shows some ions that are present in solutions, right, and what their charges correspond to what equivalents are. So, for example, if we have sodium, potassium, lithium, or ammonium ions, right, with a +1 charge, that equals 1 equivalent. Calcium, magnesium have +2 charges, so that's 2 equivalents, right? It's starting to get very, self-explanatory here. Iron, 3 equivalents, because it's got a +3 charge. What if it's an iron 2, right? Like a ferrous iron, then it would have 2 equivalents, right? Negative charges also count too, so all these like acetate and lactate, phosphate, right? Hydrogen phosphate right there, right? Chlorine, 1, -1, which is still 1 equivalent. It doesn't matter that it's negative as long as it's either plus or minus, right? Carbonate there, -2 charge, still 2 equivalents. In phosphate and citrate, minus 3 charges, still 3 equivalents, right? So let's do a really quick example question about equivalence. The laboratory tests for a patient's the laboratory test for a patient indicates a blood calcium level of 8.8 milliequivalents per liters. Okay, so how many moles of calcium ions then are present in 0.5 liters of that patient's blood? Well, this is a simple dimensional analysis problem, right? We'll start off with the fact that we know that there is 0.5 liters of blood, right? Okay. We know that there's 8.8 milliequivalents, right, per 1 liter, right? That's that right there, okay? We did that way because we need to cancel out liters to get to number of moles, right? So liters here of blood cancels, and there's liters there cancels too at the bottom. So now we need to get to now we want to cancel out milliequivalents of calcium. I forgot what ion we were looking for. Of calcium, right? That's why you should always write the ion that you're looking for in your dimensional analysis, because I almost forgot what I was doing. Right? And so to cancel out the milliequivalents of calcium, we have 1,000 milliequivalents of calcium equals 1 equivalent of calcium. We'll do our math there. We'll cancel out liters of blood, cancel out milliequivalents, and that just gives us equivalents, right? And so that gives us 0.044 equivalents of calcium. 2 ions, right? Calcium 2 ions. And then, since we have this number now, 1 mole has 2 equivalents of calcium ions, right? 1 mole has 2 equivalents of calcium ions. So we'll do 0.044 equivalents of calcium 2 for every 1 mole of Ca2 plus. There are 2 equivalents. E's are messing up there. The calcium 2 plus. So we can cancel out the calcium equivalents, right? And then it comes into just 0.044 divided by 2 equals 0.0022 moles of calcium 2 plus. Man, that's really hard to see. Write that again. There we go. 2 plus ions. All right. So now let's talk about solubility then. Right. Solubility is the maximum amount of solute that can be dissolved in a specific amount of solvent, right? And so for different solutes, the temperature will help it increase its solubility, right? So I was talking about that before with the iced tea. If the tea is still hot, the sugar actually dissolves very easily in the tea. But once it gets cold, like you put ice in it, you just have little granules of sugar at the very bottom, right? Same thing is true of salt. You can actually dissolve more salt in hot water than you'd be able to dissolve in cold water, right? So there's 2 types of, solubility, I forgot to say, is always measured in grams of solute per 100 grams of water, right? And so there's 2 types of solutions, and that is the saturated solution and the unsaturated solution, right? So we're adding salt in the water here, and the salt is the solute and it's dissolving, but you haven't reached the point at which it's saturated yet, so we call that the unsaturated solution, right? Here now, though, we've added so much salt into the water in this beaker that it begins to recrystallize at the bottom, right? At the same time that it's dissolving in the water, right? And once you get to the point where you can't dissolve any more salt in that water, it's called a saturated solution. It's called a saturated solution, right? You have undissolved solute at the bottom. Now you can get more of this salt to dissolve in the water if you heat up the water, right? And if you heat up the water and you add in salt as much as you can, get as much of it to dissolve as you can while it's hot, right? Then you've made it become what we call a supersaturated solution. Supersaturated solution. And so what's really cool about that is that once it cools down, it still remains clear, right? Like you don't see any solute in there or salt in there. But then all you have to do is add some kind of nucleation site, something that's impure, into the water, the supersaturated solution of water. And when you add it in there, everything crystallizes, and it's called a nucleation site. And then you'll see all these crystals start forming in the water, right? Because all the water starts, all the salt starts to, the supersaturated salt starts to precipitate out a solution. So it's really cool, right? It's really cool. So, as I was mentioning before, temperature actually affects the solubility of a solute, right? And in this graph here, you can see that temperature, as temperature increases, right, solubility also increases, right? So you have salt here, right? As the temperature increases, the salt solubility increases very slightly. So it's not very hard to get to salt supersaturated point, right? But other things like sodium phosphate goes up pretty readily, right? It actually has almost zero solubility. It has zero solubility in water, but when you get to boiling the water, its solubility actually increases a substantial amount, right? Here's potassium nitrate. It's almost got an exponential increase in solubility as the temperature increases. Same thing with glucose. Remember I was talking about the iced tea, right? As you heat it up, that sugar starts to dissolve, right? Potassium iodide, it's got a straight line, right? And sodium nitrate also increases its solubility as the temperature increases, right? The other thing that can affect solubility of a solute is the pressure, right? And this is actually based on something we call Henry's law. I know we've gone through a lot of laws today, but This is called Henry's Law. Henry's Law? No. Henry's Law, right? Henry's Law. And Henry's Law says that the solubility of a gas is directly related to the pressure of that gas above the liquid. Okay, so the best example of this is a Coke can, right? A Coke can is actually under pressure, right? When it's sealed, when you haven't cracked it open yet. Okay, there's lots of CO2 dissolved inside of the soda, right? Because there's pressure being exerted by the CO2 in the can against the liquid, right? There's gas above the liquid exerting pressure, and then inside the soda itself, there's more gas that's actually dissolved. But as soon as you release the pressure by cracking it open, right, the pressure above the liquid is no longer high, right? And so the CO2 starts to bubble up because it's no longer soluble because of the pressure has been released. It's a lot lower now above it, right? And now your cola or your soda, right, has a lot less CO2 inside, right? A lot less CO2 inside. So that's a practical application of Henry's Law. So now that we've talked about different types of solutions and effects of different variables like temperature and pressure and such, right? Let's talk about how we think about their concentrations, okay? So most commonly, concentrations can be measured in mass percentage, right? You can determine a mass percentage of concentration by dividing the grams of solute by the grams of solute plus the grams of the solvent itself multiplied by 100, right? That's mass by mass, or mass percent. There's also volume percent, or volume by volume, right? That's the volume of a solute divided by the volume of the solution itself, right? Times 100%, right? And then I think the most common one we use in chemistry is mass by volume percent, or M by V, mass by volume. And that's grams of solute divided by the volume of the solution itself times 100, right? Cool, right? So here we just have a picture of 0.5 grams of potassium iodide, right? And it's being dissolved in 250 mils of solution, right? So the solute here is the potassium iodide, and the solvent here, I don't know why I drew an arrow there, is the arrow, the water. Right? So we can figure out the concentration here using mass by volume, right? We have 5.0 grams of potassium iodide divided by a total solution volume of 250, right, of water solution, right? And I don't know what that is off the top of my head, so let's use the calculator real quick. I know I keep on forgetting to use the calculator on screen. Sorry about that. Clear. So 5.0 divided by 250, right, times 100. So the volume here is 2, or not the volume, the grams. The grams. Ha! The concentration here is 2% potassium iodide mass per volume, right? 2% potassium iodide mass per volume. Good stuff. In chemistry, though, we always got to be different. We use molarity as our concentration, right? And molarity is simply the number of moles of a solute divided by the 1 liter of solution, right? A liter of solution, as you can see by this equation right here, right? So 1 molar solution, a 1 molar solution of sodium chloride then is defined as 1 mole of sodium chloride dissolved in 1 liter of solution, right? So that's 1 molar sodium chloride right there, right? How do we know how many moles that is? We can use Avogadro's number and the molar mass and all that to figure out what that is in grams, right? And that's actually a huge step in chemistry, being able to go to the shelf, and I think I've said this before, but go to the shelf and get a bottle of sodium chloride off and measure out the number of grams, right? Mass out the number of grams you need to make a certain concentration of solution that can be used in an experiment. That's a really huge step in chemistry, right? So let's practice that. So we have 0.5 liters of sodium hydroxide solution, right? And it contains 6 grams of NaOH. What's its molarity then? What is its concentration then, right? Well, remember from the last slide, molarity, M, equals moles of solute over 1 liter of solution, right? Right. Well, the first thing to do is actually to convert this grams of sodium hydroxide to moles of sodium hydroxide, right? Moles of sodium hydroxide. How do we do that? Well, we've already learned this in a previous lecture. We can get the molar masses of both sodium and oxygen and hydrogen from the hydroxide ion, right? From the product table. Add them all up individually to each other, right? And so we get then that 1 mole of sodium hydroxide equals then 40 grams of sodium hydroxide. Right? 40 grams of sodium hydroxide. And that's from the molar masses of the sodium, oxygen, and the hydrogen. Right? All added together. Okay? That's good now because then we can do a quick dimensional analysis where we take 6 grams, 6.00 grams of sodium hydroxide. We want to cancel out grams of sodium hydroxide and get moles of sodium hydroxide, right? So we'll put the grams of sodium hydroxide at the bottom, which is 40 grams of NaOH. And that's 1 mole of NaOH. Grams cancel out. We're left with 6 divided by 40. So that's 0.150 moles of NaOH. Good, good. We can keep on going with this now that we have a number of moles of sodium hydroxide, right? We want to divide that by the volume we have, which is right there, 0.500 liters of NaOH. And that gives us a molarity, or concentration, of 0.3 molar sodium hydroxide. Right? So quite literally, you could go to the shelf, get a jar of solid sodium hydroxide, weigh out 6 grams of it, add that to half a liter of water, right, for a total of half a liter of water, right, and you would get a 0.3 molar solution of sodium hydroxide. Again, that's a really big deal that you're able to do this. Take something off the shelf, measure it, and figure out exactly what concentration it is. All right, so let's try that again. Let's try another one. I have here a 0.225 liters volume. I have 0.225 liters of a potassium nitrate solution. It contains 34.8 grams of potassium nitrate. So, what do I do to figure out what its molarity is? What is its molarity, right? Well, first thing to do is we have to convert the number of grams of potassium nitrate the same way we did with the sodium hydroxide to number of moles, right? So we go to the periodic table, we look up the molar mass of 1 potassium, 1 nitrogen, and 3 oxygens, right? And then so that gives us 1 mole of potassium nitrate equals 101.11 grams of potassium nitrate. Right? We want to get rid of the grams and go to moles, right? So we'll write it like this. We start out with 34.8 grams, which is in the question, of potassium nitrate. We'll put grams at the bottom so we can cancel it out. 101.11 grams potassium nitrate is equal to 1 mole of potassium nitrate. Right? Grams cancel out, leaves us with moles. So that's 34.8 divided by 101.11. And that gives us 0.344 moles of potassium nitrate. Right? And then remember this equation up here for liters for molarity, moles of solute over liter of solution. So M equals 0.344 moles of KNO3 potassium nitrate divided by 0.225 liters of solution. And our answer is then 1.53 molar solution of potassium nitrate. Fun stuff, fun stuff. Once you've got concentrations figured out, now you have to figure out how to dilute those concentrations. And we do that by using C1 V1 equals C2 V2, right? Where we have the initial concentration is C1 and the initial volume is V1, and then our concentration we're going to is C2 and the volume we're going to is V2, right? It's pretty simple. Okay? Pretty simple. So let's just go straight into doing an example. I have a volume, what volume of 2% mass by volume hydrogen chloride solution, which is actually just hydrochloric acid, can be prepared by diluting 25 mils of a 14% hydrogen chloride solution, which is also known as hydrochloric acid, right? Well, let's do some rearranging here. We know that we're looking for V2 right here. That's a V2. Okay. This is actually C2, the concentration you're going to right there, right? This is V1. And this is C1, right? So this is what you're looking for, V2, okay? So we'll get V2 by itself by rearranging the equation. So now V2 equals V1 times C 1 over C2. Right? So V2 equals then V1, which was 25 mils, right, times C1, which is 14% mass by volume, of hydrochloric acid, and C2 was 2% mass by volume, hydrochloric acid, right? Easy peasy, we cancel out percent by volume. We're left with volume, and we do the math. And that gives us 175 milliliters of solution. That's how much we can make using 25 mils of a 14% mass by volume concentration solution of hydrogen chloride, and making it that dilution at 2%, right? We're diluting 14% to 2%, right? Let's do another example. This is pretty easy. What is the molarity of a solution, right? So that's V2, I'm sorry, it's C2. That is prepared by diluting 0.18 liters, which that is V1, of a 0.6 molar hydrogen. They always say, I don't know why they say it's hydrogen nitrate, because it's actually just nitric acid. But nitric acid, so that's C1, right, to 0.54 liters, which is V2. So we're searching for V1, V2. We're searching for C2, right? So we'll rearrange the equation where C2 equals C1 times V1 over V2, right? And all we have to do here is C2 equals 0.600 molar, right? 180 for the initial volume, liters, and 0.540 liters for the final volume. And our concentration, our new concentration, is 0.2 molar. Nitric acid. Right? Nitric acid solution. And this makes sense because you had a 6 molar concentration nitric acid at 180 milliliters, or 0.18 liters. You increased it to more than half a liter, right, or 0.54 liters. So you're diluting it, which means that makes the concentration less. Good stuff. So now we're going to talk about colloids and suspensions too. We already spent a lot of time talking about solutions, and let's compare them to what colloids and suspensions are, right? A solution, as you already know, is small atoms, ions, or small molecules that are dissolved, right, as a solute in a solution, right, by a solvent. So there you don't see any particles settling to the bottom unless you've reached supersaturation, or you've reached saturation. You don't see any particles settling to the bottom, right? And since they are in solution, they can't be separated by a filter or a semi-permeable membrane, right? A semi-permeable membrane is just like a filter, except that it's got very, very, very tiny pore size for things to pass through. Very tiny, right? What is a colloid then? A colloid is made of larger molecules in a liquid, right? In some kind of liquid, and or groups of molecules. They don't settle either, right? But they can be separated by semi-permeable membranes because they are not dissolved in the solution, such as salt, for example. And then a suspension, right, is very large particles that can be seen, right? They settle rapidly, like when you put sand into water, or, for example, the iced tea with the with your sugar settling down to the bottom because it didn't dissolve because the temperature was too cold. That now becomes a suspension of salt water. Suspension of sugar in tea, salt water. Makes no sense. Anyway, these definitely can be then separated by filters, right? Separated by filters. So in this picture over here, you see a solution is represented by little orange circles, right? They're always floating, right? They're always floating in the solution, right? And then the colloids are also always floating in the solution too, right? But when you separate things out, when you put the colloid into a semi-permeable membrane here, right? The solution, the constituents of a solution, like its ions and stuff, can pass through the semi-permeable membrane easily, right? But the colloid, which is the green triangles, can't pass through, right? So you can use it to separate them out. And then the white boxes, the red boxes are a suspension which settle at the bottom, and they can easily be filtered out using a filter, right? Whereas constituents of a solution or a colloid pass straight through a filter. Okay, that's all I really need you to know about that. So now let's talk about osmotic pressure, osmosis, and reverse osmosis, right? We were just talking about a semi-permeable membrane, right, where water is a solvent, okay? And when you have sucrose in there, or sugar, right, the water passes straight through the semi-permeable membrane, but the sugar can't. It stays on one side, right? So what is osmosis then? Osmosis is the water flows into a solution from a higher, sorry, let me say that again. Water flows into the solution with a higher solute concentration until the flow of water becomes equal on both directions, right? Becomes equal on both directions. So what does that mean? That means that if you had a semi-permeable membrane, right, and there was water on both sides of that semi-permeable membrane, but on one side of it there was salt, and on the other side there was no salt, right? Osmosis occurs when the water from the side that has no salt passes through the semi-permeable membrane, right, to dilute the side with the salt in an attempt to bring the concentration of water to equal, because then there would be an equal amount of water on both sides, right? That's flowing back and forth in both directions, right? So that's what osmosis is. And so what is osmotic pressure then, right? It's basically what I just told you, right? It's equal to the pressure that would prevent any flow of additional water into more concentrated solution, right? And then it's greater as the number of dissolved particles in the solution increases. Okay. So there's a process called reverse osmosis, which most of you know as RO, because it's in water filters where you use the water filters to clean your tap water, make it drinkable with as drinkable water, right? And here in reverse osmosis, a pressure greater than the osmotic pressure is applied to the solution, forcing it through a purification membrane, right? Because generally, without that extra pressure, the water wouldn't want to pass through the membrane, right? It wouldn't want to pass through that membrane. And so the flow of the water is reversed because the water flows from an area of lower concentration water to an area of higher concentration water, right? Which is the exact opposite of what osmosis is, right? And then that brings us to our very last slide here, which is about isotonic, hypotonic, and hypertonic solutions, right? And it's all about this osmosis and osmotic pressure and the flow of water back and forth between membranes. So, as I was saying before, right, water wants to be in a situation in which its osmotic pressure is equal on both sides, right? So, if we take a red blood cell as an example, right, and we put it into an isotonic solution of, say, salt water, like, plasma, saline solution, right? Then it's perfectly fine because the concentration of salt inside the water and the concentration of salt inside the cell is equal, right? So the water doesn't need to go anywhere through any membranes, like a cell membrane, right, to equalize out the water concentration. But then, if you have a hypotonic solution, right, in a hypotonic solution, the solution is actually less salty than that of the salt concentration inside the cell, right? It's less salty. And so in an attempt to become isotonic, water will pass through the membrane of the cell, right, to try to dilute the concentration of salt inside the cell so it can become isotonic. And when that happens, the red blood cell bursts. It explodes, right? Because salt can't pass through the membrane, but water can, and that's why it's called osmosis, right? On the other end of the spectrum, we have a hypertonic solution, right, in which there is more salt in the solution than there is in the cell itself. So in an attempt to become isotonic, water from inside the cell leaves the cell, entering the solution, trying to get that to dilute down, right? And so basically what happens here is that the red blood cell dehydrates and becomes all shriveled up and shrinks. And that's what happens in a hypertonic solution, right? That's why, I don't know if you ever know, this happens to me a lot, but whenever I'm at the beach, it might be just because Galveston water is dirty. But whenever I'm at the beach, I'm in salt water all the time, And when you're in salt water, right, like the ocean water, the concentration of the ocean salt is much higher than the concentration of salt in your bodies, like your skin cells and such. So I'm always thirsty when I need water all the time. I need to drink a lot of water when I go to the beach. And the reason why is because all the water from inside my cells is leaving my cells to try to dilute the concentration of salt in the ocean. Crazy, isn't it? So that's why you're always thirsty at the ocean when you're in ocean water, like when you're at the beach. Interesting, right? Interesting. So over here, though, right, it's just another example of a semipermeable membrane. This is actually dialysis, right, where you can have a solution of salt and glucose, right, and put it into this dialysis. And the colloid solution is actually made of protein and starch, right? And if it's in this dialysis bag, the solution of salt and glucose will pass through the dialysis bag, or the membrane, into the solution. But the proteins and the starch will stay behind in the bag. And you might be asking yourself, why is that helpful? Well, it's helpful because oftentimes, uh, when you're doing a biochemistry experiment, as I am a biochemist, you want to be able to, for example, change out a buffer solution or change the solution uh, or dilute the solution without actually diluting the concentration of the protein, right? And so you can get rid of all those ions from a protein you're studying, right? But then have the protein still in the bag, right, in the dialysis bag. So that happens most commonly when you're trying to exchange buffer solutions. And buffers are just solutions that we use to maintain stability of proteins and enzymes and stuff in biochemistry.